We have learnt earlier that a capacitor is an electric circuit element that is used to store charge temporarily. It, in general, consists of two metallic plates separated and insulated from each other by a dielectric medium. Capacitors having different values of capacitances are used in power supplies, amplifiers, electric fans, motors, etc. It is not always possible to obtain capacitors with the desired values of capacitances. In such cases, the desired value of capacitance can be obtained by a combination of capacitors in a series or a parallel combination of multiple capacitors. Let us first discuss about the series combination of capacitors. Consider two parallel plate capacitors, A and B. The plates of A are labelled P and R, whereas the plates of B are labelled S and T. Let the capacitance of A be C1 and that of B be C2. The plate P of A is connected to the positive terminal of a battery, and the plate R of A is connected to the plate S of capacitor B. The plate T of B is connected to the negative terminal of the battery through a key K. This type of a combination of capacitors is called a series combination of capacitors. Let a potential difference delta V be applied across this combination by the battery. When the key is closed and the battery is connected to the combination of the capacitors, electrons are transferred out of the plate P of capacitor A and onto the plate T of capacitor B. Electrons are negatively charged and hence a negative charge is accumulated over the plate T. Let this charge be minus Q. Simultaneously, an equal amount of positive charge plus Q accumulates over the plate P. As minus Q accumulates on plate T, an equal amount of negative charge is forced off the plate S of capacitor B. Hence, the plate S has an excess positive charge, which is equal to plus Q. The negative charge, minus Q, leaving the plate S, travels through the connecting wire and accumulates on the plate R of capacitor A. Hence, the magnitude of charge accumulated on the plates of the capacitors connected in series is same. Let the potential difference across the capacitors A and B be delta V1 and delta V2 respectively. The relation between the capacitance of a capacitor C, the charge Q accumulated on it, and the potential difference across its plates delta V is given by Q is equal to C delta V. Let this be equation 1. Following the same expression, we get Q is equal to C1 delta V1 for capacitor A and Q is equal to C2 delta V2 for capacitor B. Simplifying the two expressions, we get delta V1 is equal to Q by C1 and delta V2 is equal to Q by C2. Let these be equations 2 and 3 respectively. In general, the total potential difference across any number of capacitors connected in series is the sum of the potential differences across the individual capacitors. Hence, the total potential difference offered by the battery, delta V, is equal to delta V1 plus delta V2. Let this be equation 4. Let Cs be the equivalent capacitance of the series combination of the capacitors. Then, we have charge Q is equal to Cs delta V. From this expression, we get delta V is equal to Q by Cs. Let this be equation 5. Substituting equation 5, equation 2 and equation 3 in equation 4, we get Q by Cs is equal to Q by C1 plus Q by C2. On simplifying the expression, we get 1 by Cs is equal to 1 by C1 plus 1 by C2. Let this be equation 6. The equation 6 gives the relation between the equivalent capacitance for the combination of two capacitors connected in series and their individual capacitances. The equation can be extended for any number of capacitors with different capacitance values connected in series. If n number of capacitors with capacitances C1, C2, C3, so on, up to Cn are connected in series, then the expression for equivalent capacitance of the combination Cs is given by 1 by Cs is equal to 1 by C1 plus 1 by C2 plus 1 by C3 plus so on plus 1 by Cn. Let this be equation 7. To put in words, we say that when a number of capacitors are connected in series, the reciprocal of the equivalent capacitance of the combination is equal to the sum of the reciprocals of the individual capacitances of the capacitors in the combination. Let us now discuss about capacitors connected in a parallel combination. Consider the two capacitors A and B connected to a battery that supplies a potential difference of delta V, such that the plates P and S are connected to the positive terminal of the battery and the plates R and T are connected to the negative terminal of the battery through the key. Such a combination of the capacitors is called a parallel combination of capacitors. When the key is closed, electrons are transferred through the wires and reach the plates. This transfer leaves the plates P and S positively charged and the plates R and T negatively charged. The energy required for this transfer is taken from the battery. The chemical energy stored in the battery is converted to the electrostatic potential energy associated with the separation of charge across the capacitors. The flow of charge to the plates of the capacitors stops when the plates acquire the potential difference equal to that supplied by the battery. The charge acquired by the plates of the capacitors is the maximum when the potential difference across them becomes equal to that applied. Let Q1 and Q2 be the charge accumulated on the plates of the capacitors A and B respectively. The total charge on the capacitors connected in parallel is equal to the sum of the charge on the individual capacitors. Hence, the total charge Q on both the capacitors A and B is equal to Q1 plus Q2. Let this be equation 8. As P and S are connected to the positive terminal of the battery, the potential at the plates is equal to the potential at the positive terminal of the battery. Similarly, the potential at the plates R and T is equal to the potential at the negative terminal of the battery. Hence, the potential differences across the capacitors connected in parallel are the same and is equal to the potential difference applied across the combination. Following equation 1, we have Q1 is equal to C1 delta V and Q2 is equal to C2 delta V. Let these be equations 9 and 10 respectively. Let Cp be the equivalent capacitance of the parallel combination of the capacitors. Then, we have Q is equal to Cp delta V. Let this be equation 11. Substituting equations 9, 10 and 11 in equation 8, and on simplifying, we get Cp is equal to C1 plus C2. Let this be equation 12. The equation 12 gives the relation between the equivalent capacitance for the combination of two capacitors connected in parallel and their individual capacitances. The equation can be extended for any number of capacitors with different capacitance values connected in parallel. If n number of capacitors with capacitances C1, C2, C3, so on, up to Cn are connected in parallel, then the expression for equivalent capacitance of the combination Cp is given by Cp is equal to C1 plus C2 plus C3 plus so on plus Cn. Let this be equation 13. To put in words, we say that when a number of capacitors are connected in parallel, the equivalent capacitance of the combination is equal to the sum of the individual capacitances of the capacitors in the combination.